Okay, yeah. Just a moment. Yeah, okay. So today we'll be, as I said, doing the analysis of the algorithm that we saw last time.
Sir, even yesterday I know I asked it, but I'm still a little doubtful about what does EF mean when we see that it's in residual
Just,
graph and it's not a back edge.
give me one moment. Just a moment. Okay, yeah. Now ask. Say again.
Sir, yeah, sir, yesterday in that when we said that V comma W belongs to EF, then H of V is less than equal to H of W plus 1.
Yes.
Sir, what is EF exactly?
EF is a forward or backward edge. EF is an edge in the residual graph.
Sir, but then matlab backward edge, then again that if it's of full capacity, does the backward edge still count? Because you said that backward edge can skip
Yes,
how many
yes,
levels?
it will count. Yes.
So then
So,
constraints
okay,
will
initial.
this still?
That is why I was taking the initial example, right? But will that solve your problem? If I look at the backward edge from V to S, which is there
Yes, sir.
initially, this is
Yes,
how I
sir.
had. This is where I had made this, right? That here is S.
Sir.
Everything else is below.
Yes, sir.
All the vertices are below, and there are these backward edges from all the vertices to S.
Yes, sir. They still belong in the residual graph.
Yes, they do.
So then, so is it not violated now, steepness?
No, right? Because steepness is one side only. That is what I was telling you. That H of V, now you have a V comma S edge, right?
Yes, sir.
So H of V is less than or equal to H of S plus 1. That is correct.
Okay,
And the
so it can
way
be
to
difference can be as much as
exactly anything,
okay.
whatever the difference in height is, and we'll come to what can be the heights, okay? But the point I was trying to make, and that is why I said that from this side there can be jumping edges in the backward side. From the forward
Yes, sir.
side, there can be at most one.
Yes, sir. So backward edges basically don't
Not
mean
backward
backward
edges.
normal
Like
edges.
even these
Yeah,
can be forward edges. I mean,
yeah. Okay.
backward. I mean, in the
Yes, sir.
going
Height
up.
wise.
Huh?
So height wise backward.
Exactly. Going
Okay.
up
Okay.
edges can be
That's it,
there,
sir. I
which jump
was
more.
okay. Okay. So
Yeah, but
that
they
clears it.
don't have. Yeah, the terminology might have been confusing because I might have used the term backward. But any edge which is going from lower height to upper height can jump more in the
Okay,
residual
sir.
graph, but from going from higher height to lower height, it can jump at most one.
Yes, sir. That clears it. Thank you, sir.
Okay, good. Okay, good. So today we'll be doing the analysis, running time analysis. Correctness we had done already. Okay. So now the question is going to be how many push and relabel operations, right? Because that is what we do here. We do like whenever there is a node which has some access, we take that and then we do some push and relabel, right? So how many push and relabel? Okay, good. So first, let's put the bound on relabel operation because that's easier. Okay. So the first thing is that label of S never changes throughout the algorithm. It remains H of S is equal to N, right? And the idea is that if there is, a vertex V with some axis, if EF of V is greater than 0, then the axis must come from S. And what does that mean? That in the, so we'll show a lemma that in the residual graph, there is a path from V to S, right? So let F be a preflow. Now, if V has access, then there is a path from V to S in GF, right? Okay. And how do we do this? Again, like, the similar thing that we had earlier, that let A be set of vertices reachable from S in GF, right? And now we want to show, and B is equal to, let's say, V minus A. And we want to show that all the vertices with access belong to A. Right? This is what we want to show. Is that clear, the proof strategy? So first we'll show this, and then from this, actually, the bound for a real label will follow. We'll see how. But the lemma statement is clear that if there is a preflow access at some vertex V, then there is a path from V to S, right? Okay, so all the vertices with access belong to A. That is what we want to show. And let's draw the graph. Draw a diagram. So let's say this is A, this is B, S sits somewhere here, right? Now you look at any edge which is going like this. So let's say it's going from X to Y, right? Clearly, this X to Y edge has to be like, so what can we say about this XY edge? What should be its F value? So let's say E belongs to delta plus A. What should be its F value? Remember how A and B are defined. A and B are defined in the way that A is the set of vertices reachable from S in the in GF. So what should be the flow
F
value?
is 0.
Is 0, right? Because if it is not 0, then there will be a backward edge. Sorry. So nobody pointed this out. It is not reachable from S in GF, but set of vertices that have a path to S, because that's what we want to show. Path to S in GF. And that's where we want to show that V belongs and all the vertices with access belongs, that they have a path to X, right? Where S. So X has a path to X because, like, that's how we have defined A. And now if this edge is not like fully saturated, if does not have zero pre-flow on it, then there will be a backward edge, right? And then that backward edge would mean that, this Y would also belong to, okay, let me draw it like this. Oh. Backward edge would be like this, and that would mean that Y also belongs to A. That would be a contradiction, right? So now if we just want to count the excess of B, and if we can show that that's 0 because excesses are non-negative quantities, V belongs to B, right? And if we can show that this is not like, positive, then we'll be done. And what is this? This is F in of V minus F out of V. And you sum that up over all V belongs to B. And this we know is 0. Okay, so again, so for any vertex, for any edge that is inside B, it's like, f in of V will come, it will come once on the positive side, once on the negative side. So those things will cancel out for any edge that is going inside. So if you you look at only the edges which are coming in and edges which are coming out will remain. What you'll get is E belongs to delta plus A, the going out f of E, because they will be like in for some vertex, minus summation E belongs to delta minus A, the ones which are coming out of B, f of E, right? And this we know now is 0, right? So this is minus f out of B, right?
So won't the second term also be 0? Because if there's an edge from B to A, then there's a path.
No, there is an edge. This is the flow edge, right? So if this FE is equal to CE, then this forward edge will not exist in the residual graph, right?
Okay, sir.
Okay. So we get minus f out B, and since flow is already positive for f of E is greater than or equal to 0 for all h. So we get that from this. Now this is of course this is a positive quantity. This is greater than or equal to 0. That means EF of V summation V belongs to B is equal to 0. That means B does not have any vertices with axis. Okay, good. So anything about this proof? Okay, if not, then we are done. Then we are almost done for the bound down relabel. So what the lemma says, throughout the algorithm, for all V, height of V is less than or equal to 2n minus 1. And why is this true?
Sir, because labeling only happens when there is excess at a vertex. And if there is excess at a vertex, then there will be a path from it to S.
Exactly. So if there is, some vertex with excess, then there is a path from it to S. The path can have how much length? N minus 1. S is at N already. H of S is equal to N. So how much can be the difference? Because from each edge, now there is a path in GF. So for each edge, the height can drop at most once by 1. So what has to be H of V? Less than or equal to 2n minus 1. Right? So I'm not going to write this down in detail. If there is any question, please ask.
Sir, along up the path, the height could also increase. Or sorry, also right, also increase is what I'm asking.
These can go up. That's fine. But if it goes up, okay, yeah, that's all right. Even if it goes up, but it cannot go down too much also, right? So
Yeah.
if it goes up by more than, like, if it becomes, for any vertex, if it becomes more than 2n minus 1 along the path, that node still has to reach n s. So that cannot go above 2n minus 1, right?
Yes, sir. Got it.
Any question? Okay, now, and this immediately gives, right, the bound on the relabel operation. Why? For each node, at most 2n minus 1 relabel operations. So in total, order n square. So why is this true?
Because height of every node is less than 2n minus 1.
Exactly. And the point is that labels never decrease throughout the algorithm. And that's the proof, plus previous lemma. So this gives a bound on relabeling operation. So this was the easier part. Now we have to give a bound on how many push operations are going to be there. So remember, just remember what is a push operation. We look at a vertex V such that there is somebody just one label below it, such that V has some excess, and then we push either the excess to it or we fill up the capacity of the edge, whichever gets filled first, right? Either we finish the access or we go to the capacity. And based on this distinction, we decide separate the push into two parts. So first we called what is a saturating push. So what is a saturating push? A push FHVW is saturating if either E is equal to VW is a forward edge in EF and delta is equal to C minus FE. That is, we fill it up to capacity, this edge. So suppose this was CE, right? The capacity was C, and then we flow to make it full, right? Or E is equal to, E is a backward edge, or let's say VW is a backward edge for, VW is a backward edge for E is equal to WV, right? And delta is equal to FE. Okay. So what is happening in this case? In this case, that this VW that is there is a backward edge. And actually the forward edge is this E. And F of E is the flow on this. So basically what we want to do, what is the, this saturating push operation? What is common with these two things? Can somebody tell? Is there anything common with the forward and backward edge operation in the saturating push? So in the forward edge, what did we do? We push the flow equal to CE on this edge. The flow value becomes CE. And in the backward direction, it becomes 0 for the edge E. So what does that mean? Is there something common between these two?
So that after the push, they'll not be in the residual graph.
Exactly. VW will not be in the residual graph. So that is push is saturating if after the push, the edge VW is not in GF. Okay. So in this case, VW will not be in GF because you have filled it to capacity already, so you can't push on it anymore. And here there is nothing to push back because you have put the flow value to be 0 on the edge E, and that is why there is nothing to push back from V to W. Okay? Is the definition of saturating push clear? That the edge will not remain, the edge VW will not remain in the graph, in the residue.
Yes, sir, it's clear.
Okay, good. So non-saturating push is just a push that is not saturating. But when the push is not saturating, then there is another property. What happens then? If you look at the definition of push, so in the forward direction, if this happens, then delta is this. Otherwise, this will happen. EFV. Similarly, if this happens, then it's saturating. If the second one happens, then it's saturating. And here also, if second one happens, then it's saturating. But what when the first one happens in both the cases? What is that case? We will not have. Yeah, say again, Avdesh.
The excess flow will be removed from the
Exactly.
previous.
So we will not have any excess. After the push, right? So we'll use these things to analyze things, right? So just remember this, that after a saturating push, the H does not exist. And after a non-saturating push, V does not have any excess. Okay, good. Okay, so now we are ready to analyze. So let's first put the bound on non-saturating push, okay? So the lemma is number of, okay, no, saturating is easier. Saturating pushes is less than or equal to 2nm. Okay. So let's now prove. Okay. So first thing is that, okay, let's look at a saturating push. F, H, B, W, be a saturating push. Okay. So we have seen that after the push, VW does not remain in the graph, right? So, and also what do we know? That F of V is equal to F of W plus 1. This also we know. Right? Oh, sorry, H. This also we know, right? And we know that this edge, so let's call it E. And E is not in GF, right? Good. So now the question is that how can you push on E again? If E is an edge in GF, then what has to happen now for us to push on E again? So this is the edge E in GF, let's say. And this is V, this is W, right? V does not have any excess now. And this is a saturating push. You have already put CE here, like, you know, FE is equal to CE. Right? So how can you push along this edge again? What is that situation?
Sir, along VW only or along WV as
Along
well?
VW. So VW is the edge I'm talking about.
Sir, if the height of W increases by 2, because then we can push upwards.
Exactly. So if the height of W will have to increase by 2. So if we want to push along VW again, height of W will have to increase by 2. Right? At least 2, because maybe in between V also increases or something happens. So let's say V equal to 2. And how many times height of W can increase by 2?
So n minus 1 times.
N minus 1 times. So number of times height of W can increase by 2 is n minus 1. Ever? Or let's say n to be a bad number. So it's fine. Right? So how many times we can push now along this edge? E is equal to VW n times, right? And total number of edges in G, F, is 2m that we have seen, because for every edge there can be a forward and a backward edge. So total number of saturating pushes is less than or equal to 2m. So any question about this part?
Sir, can you
Okay.
repeat why the
Why?
height of the
Sure. I didn't. So yeah, somebody answered and I didn't repeat it myself. Thank you. Thank you for reminding me. Okay, so why W's height has to increase by 2 for something to be pushed along this edge, right? So F is equal to C. This edge right now does not exist in the residual graph, right? And for it to exist in the residual graph, now there is this back edge from from W to V, and you have to push back on this edge for the flow to decrease, so that Fe value becomes less than Ce. Then only you can again push on this edge, right? So who asked the question?
sir, I did.
Okay, I did not. Okay,
Ayush.
Yeah. So I'll expect responses from you when I am explaining, at least. Okay, so that I know that you are getting what I'm saying. Okay. So
Yes.
what I'm saying is that W will have to push something back on this edge for V to be able to push on this again. Because we can push on it again only if Fe is less than Ce, and that's when E will reappear.
Yes.
Right? And when can W send something to V? When W is above V. Otherwise, W cannot send something to V. And V's height is not going to decrease definitely. So W's height has to increase by at least 2 for it to send some flow to V.
Okay. Okay. So we cannot increase because it is not possible, right? We are
No,
never
we can
increasing height.
increase. We cannot decrease is what I'm
We
saying.
cannot decrease. Okay. Yeah. We are only increasing. That's why, right?
Yeah, exactly.
Okay. So W
We
increases by
cannot
2.
decrease. So W has to increase by at least 2.
Okay. So
Maybe,
then
maybe in between V had increased already, but then W will have to increase by more than 2.
okay. So we're basically using that constraint that HW equal to HV plus 1 at greater than equal to.
Exactly.
Okay. No. I get it.
So is that clear to everybody now? Okay. So if so, now the only thing that is left is bounding the number of non-saturating pushes, right? Okay. So this is on. Yeah. Okay. Yeah. So this is this fixes the saturating pushes part, and now we have to talk about the number of non-saturating pushes. At most was it 2n square m? Okay. Or 4n square m, something like that. So what is the proof? And for this proof, we'll use something called potential method. So what is potential method? That will define some potential and we'll see how that potential changes. So generally, this kind of proof technique is used then in running time analysis, that directly you're not able to bound something, but every time something is happening, you can say that, okay, either this happens or something else happens. And every time one of these things happens, you can decrease some potential. So the potential is actually a combination of a lot of factors, such that you can always argue that in every step of the algorithm or in every step of the operation, the potential decreases. And if you have an upper bound on the potential, then if the potential keeps on decreasing, if it remains non-negative, then you have a bound on the number of steps. So you'll see that in detail, but I just wanted to give you a rough idea that what this method is. Just orally, I'm not going to there's no definition of it, so to say, but yeah. So what is the potential that we are going to define? The potential we are going to define on f and h is equal to sum the heights of v such that their axis is non-zero, right? Their axis, they have positive axis. They have some axis. So this is going to be our potential, right? And now the idea is sort of this, that okay, whenever we do a non-saturating push, some v will be taken out of this, right? But then also height increases and so on. So we also have to take into account that how does this potential function change according to other operations. So what is this potential function initially?
N.
Is this n?
Oh wait,
No.
sir, sorry, I was including source.
Okay, so no, and not n, right? It's
Yes,
zero.
sir, sorry. Yeah.
So initially, because S does not have any axis, phi fh is equal to 0, because for every other vertex, the height is 0, and S does not have any axis, right? It remains non-negative. Why it remains non-negative?
Because heights are non-negative.
Because heights are non-negative. Also, I want to claim that every non-saturating push decreases it by 1, at least 1. Why?
Because after the non-saturating push, the vertex V is still having access, but its height is increased by.
No.
Sorry.
No.
Its axis becomes 0.
Its axis becomes 0, and
So it will not come in the summation now.
again.
So it won't appear in the summation now.
But just one small point.
So that the axis which the node which axis goes to is at a lesser height.
That has non-zero height, right?
Yes, sir.
So 2 points, that V does not have access after the operation, so does not appear in the summation, and height of V is greater than or equal to 1. Right? So it was contributing something to the phi function, and now it's not contributing. So it will be removed, but also the fine point was something that this height of V was non-negative. That's why it was contributing. That's why we can say that it will definitely decrease by at least 1. Okay, good. So now we know that this operation decreases the potential by at least 1. So if we now can give an upper bound on the potential, how much the potential can go, then maybe we can do the operations and so on, give a bound on the operations. Okay, so let's see. So what about relabel? What does relabel do to potential? So relabel, let's say FHV. What does it do to the potential?
Does it increase potential because we had access? Sorry, excess.
What excess? It increases the potential by 1, right?
Yes, sir.
It just increases the height. It does not do anything else.
Yes, sir.
Why exactly 1? Right. So this is what it does. Now, what about normal, a saturating push? That is F H V W. Okay. So can it increase, decrease? What can happen? Any way it can increase? Okay, I'm telling you it can increase. Think how.
Can it increase by W's excess? Because W is having more excess.
That's because now W can get access. Earlier W did not have access, right? So W can get access, which it didn't have. So can increase by height of W, which is less than or equal to 2n minus 1. I mean, it is 2n minus 2, but let's just write 2n minus 1, right? So what is the maximum value of phi fh? Because we have bound on saturating pushes also, and we have bound on relabel operations also. So how many saturating pushes we had? Saturating push we had here 2 nm, right? So we had 2 nm for this, and for relabel, how many we had? For relabel, we had total
2n square.
order n square, yeah. So n square, right? Good. So, 2n square was it? Yeah, maybe 2n square. Or was it n square? Whatever. Right? So what is the maximum value of now phi h? Is 2n square plus 2mn plus, times 2n minus 1. Right? And this is whatever 2mn square. Should do it, right? Or some order mn square. So at most order mn square push operations, non-saturating push operations. So this finishes that how many operations are there. We have not really gone into how to implement this actually, that in the graph and so on. But in the book, if you look at that, in this much time, basically, in order one time, you can find a node with access and so on, and you can implement this in basically order mn square time. So this is the running time as well. But there is one small thing that the book mentions that I also wanted to do, which is that if in each step we choose the node with access that has highest height, largest h of v, right? Then the number of non-saturating pushes, we can give a better bound, less than or equal to 4n cube. Right here we had mn square, which can be as bad as n to the 4, but now we can do it in order n cube. Okay. So we'll prove this lemma, and then we'll be like, this is the last result for today. Okay. So how do we do this? So now let's take the potential function to be something else. So h is equal to max over all v such that excess of v is greater than 0, height of v. Okay. So let's look at this potential. Right. So does it increase or decrease by push?
It decreases.
Yeah, so it cannot increase by push, right? H cannot increase by push operation. Be it saturating push or non-saturating push and so on. Can only increase by relabel. Right? Good. So how many times H can increase? 2n square, because it only increases by relabel operations. So 2n square times can increase. Right? And it remains non-negative. So now I want to give the bound on how many times H can change. I claim that H can change total 4n square times. Why this is true? I mean, at most. So H increases 2n square times, and I'm saying that H can change at most 4n square times. Why? So it can increase or it can decrease, right? If it decreases also, it decreases by at least 1. So what happens if H changes more than 4n square times? Hello, am I audible?
Yes, sir.
Okay, good. What happened? All right. Can you see my screen as well?
No, sir, your screen is not visible.
Something Okay, so anyway, my question is there that if h can increase only these many times, why h can change at most 4n square times? So if h changes more than 4n square times, then h decreases more than 2n square times, right? Because h can increase at most 2n square times. Okay, what is the problem? Just a moment. This. Hmm. Okay, so anyway, let me just share this screen itself, and then maybe we can. That thing hand. Okay, all right. Cannot. Okay, just a moment. Okay, maybe it will work. All right. So hopefully you can see that now, the screen. Can you?
Yes, sir.
Okay, good. So let's do this quickly. So what I was saying that h can change at most 4n square time, because if not, then h decreases greater than 4n square 2n square times, because h increases at most 2n square times, and which will make h negative, which is not possible. Right? So h changes at most 4n square times. Good. Now what happens when h remains the same? Right? So the claim is that in this phase, when h remains the same, each node can have at most one non-saturating push. Okay, each node can have at most one non-saturating push when h remains the same, right? And why is that true? Because you look at some non-saturating push from V to W, let's say, and suppose now h, so V was at h, right? That's how or h remains constant, right? So suppose h was to change again. So for V, if we want to push again, right? So V was the node at highest height, right? That is what we started with. That is our assumption. that what do we do in this operation? We start with we always push from the node with the highest height. So V is at height h, right? So now if we want to push from V again, and this is a non-saturating push, right? But if we want to push from V again, V does not have any access after the non-saturating push. So how can we push from V again? What would have to happen for pushing from V again? Anyone? Ayush, Santak, Avdesh, Amit, anybody?
We need
So in
two
order,
variables on W.
Say again.
We need
Okay,
two
so
variables.
yeah, Mrityunjay, say again. Sorry. We need.
We need two relayables on W and then again two relayables on V.
Okay, we might not need relabels on V. Oh, yeah, that is also true. That's correct. But okay, Ayush, you were also saying something?
No, sir, I wasn't. I think Amit or somebody else was.
Okay, Amit or Santak, were you? Okay, anyway, the point is that H will have to change. Something will have to go above V to give some excess flow to V such that we can, and V is already at the highest height, that is H. That means something will have to go above V, either W or some other vertex to give V some excess flow, right? So that's what we wanted to say, that each node can have at most one non-saturating push when H remains constant. Sorry, capital H remains constant. So H will have to change. So that means if H remains constant, we can have just one flow from each of the vertices. And that's it. We know that how many times H can change? H can change at most 4n square times. And when H remains constant, we can push at most once, right? So so for each vertex, there can be at most 4n square non-saturating pushes throughout the algorithm. And hence the total number of pushes, non-saturating pushes, less than or equal to 4n cube, because there are n vertices. Okay. And similarly, this is so this gives another running time. So running time basically turns out to be order n square m by if you use the normal one, or order n cube using this one. So any question about this last part where we chose this vertex with the highest height to push from? So the point was there were two parts. The first part was that it can only increase. It can increase only by relabel operations. There is a bound on relabel operations, so that gives us a bound on how many times it can change. And then when it remains constant, then what happens? Then we can push at most once from a vertex, and that gives us the total bound. Okay. So this finishes our discussion of preflow push now. And you see that these bounds are independent of C as we wanted them to be. That is why we were discussing the preflow push operation, that the running time is not depending on C. It is like strongly polynomial. It just depends on N and M and is polynomial in N and M. And now in the next lecture, we'll see some applications of this flow, max flow techniques and so on. Okay. So any questions, anything? Okay, if not, then see you guys next week. Yeah, tell me. Yeah, there was a question. Tell me.
Sir, I have a question not related to the course though. So,
Okay,
can I ask it now or?
go ahead.
Sir, next time we'll be taking the course ML 760, right?
Yes.
Sir, so as of now, it is floated as an open elective for us and not
Okay.
as the department elective. So, do you have any idea about it?
No, I don't have. This question was asked yesterday also, so I would request you to send an email to Professor Minati. She is the coordinator, and Professor Dhanraja maybe. And
Okay.
see. I don't know about it. Okay. Thank you.
Yeah, okay. Thanks a lot, sir.